Okay, guys, so now we are going to be doing a review. So from every chapter, I'm going to be picking in some of the very important concepts that you need to focus on for your final exam. And I'm expecting that by this time you already know the theory because we covered it in great details, in worksheets, homeworks, you got practice on that, and you got practice through your midterm exams and extra credit. So that is why I'm going to be doing this review. Like, we just have very short period of time to cover all the 10, 11 chapters. And what is important is that as I'm doing the review, you are going to be also doing it from your end. So this is going to be a practice for you. In case you don't understand something, you can always stop and ask, okay? But if you're just sitting there and just observing, this might not help you. So I expect that when we are doing the questions here on the board, you are going to be doing questions on a sheet of paper, doing the calculations and putting your response in the chat. So this is like your classroom participation. And like I said, if you don't understand something, please stop me right there and I'm going to explain this to you again. But hopefully this is we can finish all of this, like a good practice for you guys, and prepares you for the test. Okay, so right now I'm just muting all, but you can unmute and then give your response also. You can talk also, that's fine. Okay, but it just, I want to slow down the background noise, that's why. Okay, so you can unmute and talk from your side. All right, guys? Okay, all right. So here we go. First of all, what is important in chapter on the acid bases? So we already talked about titration, and let's just do some of these questions that relate to titration. Okay, acid base titrations, we covered like what the process is. Let's look at this thing. A solution of 0.204, let me write this down. So what is given to you? 0.204 molar NaOH. This is given. So NaOH is a base. Okay. NaOH is used to titrate 50 milliliters of, so volume. So volume given is, that's the molarity, and the volume given is 50 milliliters, 50.0 milliliters of H3PO4, H3PO4, and this is a acid, H3PO4, which is 0.0224 molar. Okay, so this acid is H3PO4, and this is being titrated with a base, which is, the molarity given is of NaOH is 0.204 molar. What is the volume in milliliters? Now they want you to find the volume in milliliters. So pay attention to that. Milliliters of NaOH solution. Okay, so here's the reaction. H3PO4 aqueous is reacting with NaOH. NaOH, and this is also aqueous, and this is giving you Na3PO4, and this is also aqueous, and this is giving you water, H2O, and water is a liquid. So always, first thing for these type of questions, you're going to write down what is given to you. Second thing is you're going to write down the equation if that's needed, and always check the equation. So let's check the equation first of all, and this also includes the balancing of the equations. So if you look at it, there are 3 hydrogens here. There is, keep the phosphate ions together. So this is the phosphate ions, 1 phosphate ions, 3 hydrogen ions, and you have 1 sodium ion, and you have 1 OH ion, and you have 3 sodium ions, and you have 1 phosphate ion here, and you have water, although we don't, ionize water. So there are 3 hydrogen atoms and 1 oxygen here. Okay, so now comes the question that what is not balanced? So if you look at it, that sodium is 1 here, sodium is 3 here, right? And another thing that is not balanced is the, pretty much, yeah, so maybe oxygen. So let's look at this. So sodium is 3 on one side, so you will have to add 3 here. Okay, so now this makes 3 sodium. So 3 times 1 is equal to 3 sodiums, and 3 times 1 OH makes it 3 OH ions. So now let's calculate this, all of it. So we have we have one phosphate, three sodiums. Now calculate the hydrogens. Hydrogens are three hydrogens are fine. What about oxygens? So there's only one oxygen here, whereas how many oxygens are on this side? Three oxygens. So how are you going to make it three? Sorry, this is two waters, my mistake here, sorry. This is two hydrogens, okay? So how do we make this? So two hydrogens here, three hydrogens here. So obviously hydrogens are not balanced, right? Hydrogens is not balanced. So what do we do? Tell me. Three hydrogens on one side, three hydrogens here, two hydrogens this side, three oxygens here, one oxygen here. So how do we balance this? Let's see. Oh, am I not screen sharing? Wait a minute.
I can see it.
Can you guys see the screen?
Yes.
Okay, so, okay, good. All right, so if you put three
No, I'm
here,
so sorry.
yeah, three here, so this becomes 3 times 2, 3 times, so this becomes 6 hydrogens, this is 3 oxygens, and so we have 3 oxygens and we have 3 hydrogens here, and total hydrogens are 6 hydrogens, 3 from here, 3 from here, 6 hydrogens. So 6 hydrogens is balanced, 3 oxygens and 3 oxygens are balanced. Okay, so it's very important you balance the equation. So right now I'm not going to repeat the balancing. I may repeat in some other questions, but let's move on from here. So what are the first steps? Oh, okay, so for titration, always remember that the first step is going to be, you need to find the moles. Obviously, first, let's just do the conversion from milliliters to liters. Milliliters to liters, that's the first thing. Second thing is, yeah, so second thing is you take the moles of whatever is given to you. In this case, the acid is given. Take the moles of acid, find the moles of acid. How many? So you are given the molarity. Molarity is equal to moles over the volume of the solution in liters. Okay, so the moles is equal to molarity times the volume in liters. This is the reason why you need to convert the volume in liters. Okay, so this is going to be the moles of the, in this case, the moles of the acid. Then next thing is you're going to find the moles of the base. And how do you do that? That's where you're balancing the equation. That's the mole to mole ratio comes into play. So the moles of the acid you already know. You can, from that, you can find the moles of the base. So once you have the moles of the base, you can find the molarity, base, moles of the base, you can find the molarity. And how do you do that? Molarity is equal to moles over the volume in liters. And this is the reason why we need to convert the volume. In this case, the molarity is given. We need to find, in this situation, the molarity is given, moles over the molarity. So in case, generally, this is a different example I took. Generally, we use the titration to find the molarity of the unknown, okay? Unknown acid or an unknown base. So when once you get the moles, you take the volume and you find the molarity. Or if the volume needs to be found out, let us just say for the sake of doing this problems, if the volume needs to be found out, then we already know the molarity, then you can use this formula. So this formula is if you need to find the molarity, this second formula is if you need to find the volume. Okay, let's start doing this. So first step is to convert the milliliters to liters, and that is, we are given how much? 50 milliliters of H3PO4. So H3PO4, 50.0 milliliters times. Now liters. 1 liter over 1,000 milliliters.
Liters. Let's
Remember
see,
that?
that would be
1,000
0.5.
milliliters is equal to 1 liter. Okay. So what do you get here? 0.050 liters. Okay. So this is first step. Second step is, the second step is to find the moles of the acid. So we have the molarity 0.0224. So 0.0224 m. Okay, molarity. And the volume we already have. The molarity times the volume is 0.050 liters, and the moles of the acid is going to be, and this gives the H3PO4, H3PO4. So what do you get here? You guys do the calculations and tell me.
Getting it. Speak times 0.05. 0.00112.
0.00112 moles of H3PO4. Okay. Next, third step. Once you get the moles of the you find the moles of the base, right? You're going to find the moles of the base. Now you're going to look at the relationship here. The relationship is that the acid is only 1 mole. The base is 3 moles. So 1 to 3 relationship. So we know the moles of the acid 0.00112 moles of the acid, which is H3PO4, okay, times. Now we need to find the moles of the base. And from the equation, we see 3 moles of NaOH are reacting with 1 mole of H3PO4, 1 mole of H3PO4. So what do you get here?
0.00336.
336 moles, and these are the moles of NaOH. Okay, so next step is you have the moles of NaOH. You have the molarity of NaOH, which is 0.204 molar. So molarity is 0.204 molar is the molarity of NaOH, and the moles of NaOH given is, or we found out is 0.00336. Okay, so how do you find the volume? So volume in liters, remember this is going to be in liters, is equal to moles of NaOH in this case over the molarity of NaOH, molarity of NaOH. So do this 0.00336 divided by the molarity 0.204 m. What do you get?
0.016.
0.016.
47.
0.01647 liters. Okay,
yeah.
So liters, but pay attention to the details. The question is asking you convert this to milliliters.
Oh, okay. Yeah, thank you. So times by 1,000, right?
We need to convert
so
this.
16.47.
16.47. Yeah. So next step, the last step is you could take the liters and convert that to milliliters. So we know that 1 liter is equal to 1,000 milliliters. And so 0.01647 liters times 1,000 milliliters over 1 liter. So if you look at it, this liter and this liter cancels out. And then what do you get here? 16.47. So I see some students have it as 16. So Mohammed, you have 0.1647. Can you check? Mohammed, just check your answer, okay? Just double check and let me know if you get anything different. Okay, so anyway, so this becomes 16.47 milliliters. So this is what you need to pay attention in the
Oh, milliliters. Oh, so sorry. You wanted the unit of measurement.
unit. Yeah. Okay, got it, Norman? Good. Okay. So this is, so pay attention to these. These are the details where students make the mistake. Generally, maybe they're doing all the right working, but they don't choose the right response in the multiple choice. You
Oh,
know,
yeah.
multiple choice, you may have this as a liter and this as a milliliter. So pay attention to that. Don't get like, so
Yeah.
the detail. If the answer is in liters, then you choose this, the one I'm highlighting in yellow. Okay. So I'm just letting you know that what I'm telling you, there is going to be a question on titration. So you practice, practice, practice. Okay, guys, practice it. This is very important. Generally, there is a lab, but you know, actual lab, but you guys had done the labs in the simulations. You have an idea. Okay. Anyway, so one question is that. Next question is going to be on the transfer reaction. So let me just write this down here. This is number one, titration. Number two is the transfer reactions. So here is your, these are also called the proton transfer reactions. Okay, proton transfer reaction, and these are also called the you know, a transfer, or these are also called these equilibrium reaction. Tell what is the direction of the equilibrium. Direction of the equilibrium.
Equilibrium.
Yeah. So let's look at some of the
You
examples.
first need to know which is the stronger base and the stronger acid and what side it's on. So
Yeah, and stronger conjugate. Yeah, conjugate. So you will be comparing an acid to a conjugate acid and a base to a conjugate base. Okay, so let us look at this example here. 1 minute. Uh, strengths of the acids. Yeah. So here's a question. Okay, so sometimes the question is given. Okay, there's another thing. I'm also, the questions that I'm doing from the book, let me just label them so that you have an idea which ones we're doing. So this question I did, the one on the titration was the one on, 1 minute, the one I did on, okay, this was 11.65. So I'm going to just label the questions here. So this question was 11.65, and this is page 427. Page 427. So some of these questions might just come out to be your homework questions. So, you know, in a way, this is like a review. Okay, now let's look at this question, 11.24, 11.24, and this is page number 411. Okay, so now here we have, now the question is asking, the way it is, the way it's referenced or said is, predict whether each of the following reaction contains mostly the reactants or the products. Okay, so nowhere there is a reference to proton transfer reaction. I mean, the question is not referencing this. The question is also not saying what is the direction of the equilibrium, but it is implied. So that's why. So look at this question. Okay, predict whether each of the following reactions. So let me write this down here. Predict. I mean, come on, you don't have to predict, you have to actually do it, right? So we have to actually do. So I don't, when I'm putting my questions, I never say predict, you know, you actually say, you know, identify, you do it. So that's why you have to do it. So identify whether each of the following reactions contain mostly reactants. Are there going to be mostly reactants, or are there going to be mostly products? Okay, are there mostly reactants or they're mostly products in this reaction? So what they are saying is, if there are mostly reactants, that means the reaction is moving backwards. The reaction is moving backwards if it is so backward, or the reaction is reverse if they are mostly reactants, you know. On the other hand, if they are mostly products, that means the reaction is moving forward. and the reaction is like you know, it's moving forward, moving reaction. So a reverse reaction moves from right to left, and a forward reaction moves from no, sorry, a reverse reaction moves from left to right. Sorry, left. No, wait 1 second. Backward reaction is going to move from the left to right. In other words, from the reactant, from the products to the reactant side. Okay, so put it that way. So react from the products to the, and the forward reaction is moving from the reactants to the product side. So that's what it is. Okay, now let's look at this reaction here. One, you are given H3PO4, okay, and this is aqueous, and this is reacting with water, and that is in a liquid state. And here's your equilibrium, and here's your hydronium ion, and this is aqueous, and you have H2PO4 negative, and
We
that's
know this is the base.
okay.
The first element is acid, second element is base. Then in the next side of things, we have conjugated acid, hydrogen, free O, and then the conjugated base to that would, in that side, the reaction would be H2 phosphate. So let's look at strengths.
Yeah.
Neutral.
Yeah. So pay attention to this, guys. If you don't see here, look, remember, no proton transfer has been mentioned and no direction of the equilibrium has been mentioned, but that is what you need to find. Okay. So the question is simply asking, are there mostly reactants, or is the concentration of the reactants or the concentration of the products, which one is more? Concentration of the reactants or the concentration of the products? Okay, so this is what you're going to look at, whether the reaction is moving backward or forward. So here's the formula, that strong, the direction of the equilibrium is going to be from the strong to the weaker side, from the rather stronger, from the stronger to the weaker side. Okay, so here you have the H3PO4 aqueous, water. So remember, water, we never identify it as an acid or a base. Don't start with that because it's confusing. Water is amphoteric. It can be acid, it can be base. So when the proton is transferred in an equilibrium reaction, it's going to move from a stronger side. So water could be stronger acid, water could be stronger base, water could be weaker acid, water could be weaker base. So it's why water is tricky. You need to look at what is it reacting with and which side is a stronger side. If the side, whichever side is a stronger, then the direction of the equilibrium is going to be opposite of that side. It's going to move towards the weaker side. So here you're going to look at the acid, identify the acid and a conjugate base, and identify a base and then its conjugate acid. So this is the first step. The second step is going to be, the second step is the
weak base.
Compare using the table. Remember, there is a table, and if you guys don't, you are allowed to use these handouts, and here is this table that you're going to use. Okay, this is the table, and in this table you are going to look at, you're going to compare an acid to the conjugate acid, and you're going to compare base to the conjugate base, and then whichever side is stronger, you identify the stronger side, and then just move the direction of the equilibrium, like a big arrow that side is a small arrow going backward, or whichever way, you know. So this is going to be from a stronger to the weaker side. And that is where the proton is being transferred, the hydrogen ions are being transferred. So in this case, let's look at it. So we have H3PO4. Now tell me, what is H3PO4 to you? What is H3PO4?
That would be the weaker acid.
No, for now, don't look at whether it's a weak or acid. For just tell, what is H3PO4 to you?
It's an acid.
Acid, right? So this, if H3PO4 is acting as an acid, then in that case, the water will have to act as a base. So that's why I'm saying, you know, pay very attention to, do not start from here. Do not start from water, because like I said, Water is amphoteric in nature. Amphoteric means it could be acid or a base. So you should look at the other element or the others, other
Yeah.
species that is in here. So we have now H3PO4, water, and this is giving you hydronium ion. And now tell me, what is a hydronium ion in this case? What is hydronium ion?
In this case, tritium ion.
Conjugate acid or a conjugate base, and of what?
H3O would be the conjugated acid
Of, yes, it is a conjugate acid
of H2O.
H2O. Excellent. So this is the conjugate acid of, always they come from, you know, a parent, conjugate acid of H2O. And what about H2PO4 negative?
That would be the conjugated base of
Conjugate base of H3PO4. Remember, one less hydrogen ion. Okay. So now we have identified. That's your first step. That's the first step. Second step is now you're going to compare H3PO4 versus the conjugate acid H3O plus, and you're going to look at the table. And in that table, this is the table 11.3. Okay, 11.3. So look at which one is stronger. And then similarly, you compare water, which is acting as a base in this case, with the conjugate base, which is H2PO4, sorry, H2PO4 negative. All right, now tell me, which one is stronger?
Yeah. So stronger elements, or I mean, sorry, strongy acid and bases would be on the right side.
Yeah, so if you look at this table right here, look at this table. So in this table, you see that you have the bases on this side and the acids are on this side. The strong acids are all on the top. The weak acids are all at the bottom, and the ones in the middle are like kind of in the middle. The bases, these ones on the top are weak bases. And these guys here on the bottom are strong bases. So compare now H3PO4 and H3O on the acid side. On the acid side, tell me, so H3O and H3PO4, where are they placed?
H3O stronger.
H3O and H3PO4, yeah. So H3O, so if you look at it, the H3O is, if I'm not, where's my pen? H3O, right? It's above, it's towards the stronger side. And H3PO4 is here, right here, somewhere in this lower, like lower than that. So H3PO4 is weaker than H3O plus. So this is weaker. H3PO4 is weaker acid than the hydronium ion. Hydronium ion is stronger in comparison. Okay. Next is compare water and H2PO4. Water. Now you're going to look on the basic side because you're comparing the base. So look at water and H2PO4 negative. Which one is stronger? Water and H2PO4 negative. Which one is stronger?
H2O.
No, that's weaker because base strength, it's as it goes down.
Oh,
Yeah,
right,
see, here's the thing, interesting part. Water can be found on the acidic side, water is found on the basic side also. So if you're looking at the acids, like if you're comparing an acid, then look at the conjugate acid. If you're comparing a base, look at the conjugate base. So base on one side, acid on one side. And here we see water is, although, yeah, remember this is on the base side, this is a weaker side, this side is a weaker side, okay? And this side is all stronger, it's moving stronger. So if you compare H2PO4 is stronger than H2O. So in comparison, H2O is weaker. base than the dihydrogen phosphate ion. So, so dihydrogen phosphate ion is stronger than water. Okay, so yeah, so that's good. So everybody got that, how to use the table?
Yeah.
Yeah, so there is going to be a question on that. So just don't make a mistake, because generally water is the one that is kind of, you know, like tricks people. But if you just compare base to a base and acid to acid, then you can't go wrong. Okay. Now you are going to come. Now we identified which is weaker. So now you're going to place this here. Place this. So we see H3PO4 plus H2O and H3O plus and H2PO4 negative. And now we are going to place the which one was the stronger hydronium ion. So this is stronger. H2PO4 negative, this ion is also stronger. In comparison, this is weaker and water is also weaker. So what is the direction of the equilibrium here? Direction of the equilibrium according to the formula? It's right there on your screen.
Dang it.
Moving from where?
Let's see.
Look at the formula, guys. Yeah. What is, where is the formula looking, moving from? From where to where? What does it tell you? Come on.
Oh,
Okay, today
it's moving from weaker to stronger, so that would be mostly reactants.
no, wait, maybe did I not? Okay, maybe I wasn't clear. Okay, here, right here. Okay, moving from here. Although it's like it's going to still be at the equilibrium, but majority of it is going to move from a stronger to a weaker side. Okay, and then a little bit is going here, back. So stronger to a weaker side, and here also stronger. I made a. This is not the same arrow, but here. Okay, now tell me. Maybe that's better. Tell me now, which side? Moving from the stronger.
To, the weaker to the stronger.
Yeah, no, is stronger to weaker.
Yes,
Not weaker to stronger. Stronger to weaker.
weaker to stronger.
Like the arrow, look at the direction of arrow. Big arrow going back.
Oh, yeah, sorry.
But it's still at equilibrium, right? But it's the one side is going to be like more pronounced. So the direction of the equilibrium is going to be, in this case, from the stronger to the weaker side. So this is what it is. Okay. And this, oh. Okay, here. And then. So moving backwards. Okay. Moving backward. Okay, guys. Clear? Stronger to weaker. Okay. Now we have, so that's all you need to say. Now comes the question. The question is asking a little bit more in depth that what is there going to be? Mostly reactants or is it mostly product? So if there are, like if it's moving backwards, that means where? If it is moving backwards, what is more? The reactants?
Mostly reactants.
Yeah. This side is the reactants. These are the reactants. I mean, you know, equilibrium, that's why it's a little bit confusing because still we consider it from our side. These guys are the reactants and these on the other side are the products. So what we do here is that the reactants are more than the product. The concentration is shown by the square brackets and we see that the reactants are more than the products. Okay, clear? Any questions so far? Everyone?
Yeah, I'm getting it.
Getting it? Do you want to do one more? Let's do one more.
Yes, please.
Yeah, let's, yeah.
Let's Do one more. Okay, then let's look at the second question, which is B. Okay, B. So this one was the part, this is part A. This is part A, and this is part B. So here again, this is the carbonate ion. So here is your carbonate ion, aqueous, reacting with water. Now pay attention to this carbonate ion and water. You know, water can be acid, water can be base. So don't start with just with that. Look at some other identifiers. So here's your OH ions, and then you have the bicarbonate ions, CO3 negative. So certain things you should already know, that, you know, like OH ions always is just going to be basic. Nothing. So you identified a base here. Which one is a base in this
The
reaction?
base in this case would be the carbon trioxide. Let's see now.
No, okay.
The OH.
OH, yes. OH ions, always basic, always.
Yeah.
So I'm going to just put here a note here that anytime you have OH ions are always going to be, that means that is a base, or it is coming from a base, or OH ions makes a solution basic. So that's what it is, or OH ions are bases. So you have identified a base. If you identified a base, the next thing is this has to be an acid. Clear? That's clear, right? So you always OH ions you see somewhere, always base. So don't forget that. Okay, and then the rest component is an acid. Now comes the next part. Identify the conjugate acid and the conjugate base. Which one is the conjugate acid and which one is the conjugate base now on the other side, which is the carbonate and the water. So you are comparing carbonate ion to the bicarbonate, because that's where it's coming from, you know, carbonate, bicarbonate. Next is you're going to compare H2O and OH. So how did bicarbonate, so how did the bicarbonate happen, or what happened here? What do you think? If bicarbonate is acting as an acid, right? Bicarbonate is acting as an acid, then the carbonate is going to be, let me flip it.
Carbonate is going to be
Let me flip it. Yeah.
the
Okay. Here.
base. Yeah, the carbonate is going to be the base.
O2 negative is giving you carbonate ions, negative. And then here you have the OH ion, negative, and H2O. So how does this happen? Bicarbonate gave what? What did bicarbonate give? To make carbonate. Come on, guys, write it down.
The bicarbonate gave one of its hydrogens, to the H2O.
No, yeah, bicarbonate
making it
hydrogens. Yeah, so minus
making that a base acid. So H2O would be base.
Oh, sorry. Okay, here's your OH ions and the water ion. So OH ions, add that one hydrogen ion. Okay, so this is, if this is acting as an acid, this is the conjugate base of HCO3 negative. OH ion, okay, is acting as a base. That means the water is the conjugate acid. Okay, if this is a base, and then this is the conjugate acid of OH ions. Okay, this was the first step. That's the second step. And then, sorry, this should be 1. This is happening here. Okay, this is the first step. This is the second step. Third step. Now you're going to compare. Okay, an acid, conjugate acid, and an acid, and you're going to compare a conjugate base to a base. So in other words, you're going to compare HCO3 negative to the water, and you're going to compare OH ions to the conjugate base, wait a minute, base, yeah, to carbonate ions. Carbonate ions. So which one is stronger? Which one is stronger? Look at the table, 11.3. Okay, and now you guys tell me. Water to bicarbonate and carbonate to OH ions. Look in the periodic, look in the table. Look in the table, guys. Where do you see OH, first of all? Tell me, where do you see OH?
Be
HCO
OH.
is stronger than water. Okay, from the table. And Anthony, what about the OH? Where is OH? Negative. OH is stronger than carbonate. Very good. So this is stronger, and this one is stronger.
Yeah.
This is weaker according to the table, and this is also weaker. All right, so now we have, that means now we can just write down the equation again, which is, let me just write this down again. Carbonate CO3 negative 2 plus H2O. H2O, this is aqueous. Actually, this is liquid. Liquid. This is aqueous, and this gives you OH ions, and this is aqueous, and HCO3 negative aqueous. Okay, so here we have the carbonate and the water and OH ions and the bicarbonate. So what do we do here now? We are going to just place them and identify like what is the direction of this equilibrium. So this is strong, stronger, this is stronger, as we have identified from the table. This is weaker, and this is also weaker. So what is the direction of the equilibrium? Backwards. Okay, so we will see this here is backwards is this way. Like that, and instead of going forward. So there are more reactants. In other words, the concentration of the reactants is more than the concentration of the product. So the question is asking, which one has a more concentration, reactants or the products? But you have to go through all this process to identify that. Okay, and another question can be asked, is the reaction moving forward or backward? The reaction is moving backward. Okay, so these are the questions that I'm just letting you know upfront that this is important and this is going to be on the test. So proton transfer. So just make sure that you read the table correctly and don't start with water. And anytime you have, here's a trick, anytime you have OH present, anytime you have an OH present, it's always going to be a strong base, always. There's no question asked. And anytime you identify, so that's what I'm saying, anytime either you identify a base or you identify an acid. So base, OH ion present anytime will be base. Acid, you will always have, like, you need to recognize them, start memorizing their names, or you should know that another thing for the acids is always hydrogen. Generally for inorganic acids, the hydrogen is going to be in front. Organic acids, it is the COOH group that makes them organic. But mostly we are looking at the inorganic acids. So hydrogen is always in front for the acid. I mean, in general, if you look at it, that when you're comparing, This is an acid hydrogen front. This is also acting as a acid. Okay, so you know with that's anytime hydrogen will, it has to be in front. So like this, why this guy cannot be an acid? Why? Because it's not going to liberate hydrogen ions. A carbonate ion doesn't have a hydrogen ion. So that's the condition for anything to be an acid, whether it's an acid or a conjugate acid even. It has to give away hydrogen ions, or it should have a large excess of hydrogen ions. So if you look at this, this is a base. Right here is a base. And this hydrogen ion is at the back, not in front. But this is acting as an acid because the hydrogen is in front. Okay, so keep that in mind that for the acids, they will have lots of hydrogen ions. And even if there's only one hydrogen ion, for example, in this case, look at this, one hydrogen ion, no hydrogens. That is why it has to be a base. This guy acting in front, hydrogen in front, acid, okay? So this is the very basic for these proton transfer reactions. Direction of the equilibrium, and then questions regarding, you know, identify the conjugate acid base pair. Let's just do some questions here. Identify the conjugate acid base pairs. One more question. Here's, sorry, this one, page 406, and identify conjugate acid base pair in a reaction. Okay, so here we have like, for example, let's do this problem. Identify the base in each of the following. So I'm going to do this one, 11.14. Okay, 11 point, identify the stronger acid base pairs in the following equations. For example, you have this H, yeah, let's do this one. Sorry, 11.14 is, it just counted. Okay, let's do this. H, this is D, part B. Part D. And here part D is HNO2 aqueous. Okay, plus CH3, CH2, NH2. Okay, and this again at equilibrium. And we have to find out the conjugate acid base pairs here. So we'll find. So here you have CH3, CH2, NH4. No, sorry, NH3 plus, and you have NO2 negative, NO2 negative. Okay, and so this guy is aqueous also. This one's aqueous, and this one is also aqueous. All right, now we have the nitrous acid, and they're saying identify the conjugate acid base pair. So that's same story. You will have to first start with anything that you can identify, like you can look at like apparently something that looks like an acid to you or looks like a base to you. And then every acid will have a conjugate base, and every base will have a conjugate acid. Okay?
Yeah, so we know the first thing, the hydrogen nitrate would be an acid.
Okay, yeah, so yeah, that's right, Joshua. So HNO2. So this is the this is not hydrogen nitrate, it's a nitrous acid. Okay,
Nitrous, sorry.
nitrous, yeah, nitrous. Remember, nitric is HNO3. So this is NITROUS, less oxygens, nitrous acid.
Yeah.
Okay, and then this one, you don't worry about this. These are organic compounds, but interesting part here is we can always, this is kind of like carbon hydrogen bonds, kind of non-reactive, and they're just there like as a, just to give a structure to the molecule. But our real active site in this molecule is this, NO2, NH2, sorry, NH2 becomes NH3 plus. So that's where the reactivity is, okay? So that's that part. So it's okay for generally for the organic compounds also. We can assume that these right here are, can be considered as R. R means rest of the molecule. okay, molecule, and that it can be shown as R because it's non-reactive. So we are only focusing on the NH2 becoming NH3 and giving away the. So tell me now. So acid we identified as HNO2. So what is the conjugate base of HNO2? HNO2 conjugate base. Which one is that? Remember acid base, the
NO2.
NO2, very good. Minus one hydrogen ion. And this becomes NO.
Amide.
And which one is acting as a base now? Which is the base in this reaction? This guy, CH3CH2 NH2. This will act as a base. Okay, so anytime you identify an acid or a base, like the counterpart is going to be, you know, the acid, a base or an acid. Okay, so NH2 is the acting as a base. Then what is the conjugate acid of this molecule? What is the conjugate acid?
NO2.
No, conjugate acid.
So
Acid, always there's going to be more hydrogens in acid, first of all. Anything that is acidic. So look on the other side.
the NH3.
NH3 plus, very good. So this is CH3CH2, and it's sufficient to say it R, but this is NH3 plus. It's weird, right? But that is what it is, conjugate acid. So here is it. So this one in a base, this has added that one hydrogen ion, which was given by the acid HNO2. Okay, so then it forms. So this is what the question is simply asking. Identify the conjugate acid-base pair. So just keep in mind that the acids, some of the common names acid you should know, you know, by this time. So sort of memorize it. But once you identify the acid, the other guy will have to be, whether you recognize it or not. I mean, in general, you know that nitrogen-containing compound. Okay, Joshua, just a minute. Okay, so nitrogen-containing compounds, especially, you know, with if they have nitrogen, hydrogen, like they would be have a basic nature to it. Okay, base also means giving away electrons. So that also, it's a weak base, but you know, OH is anything that contains OH is a strong base, but anything that does not contain nitrogen, OH ions, but it gives away the electrons, it will still act basic in nature. Giving away electrons is basic. Giving away protons is an acid. So here, this is a proton. Giving away a proton. This is a proton. Sorry. Hydrogen ions, protons, okay? And so that is why HNO2 acts as a base, as an acid, sorry, okay? All right, so this type of question, again, you know, identify the acid-base pairing. So it is just one hydrogen ion. So this is again, test question, okay? Another type of test questions can be also, how do you identify whether in this reaction, there are more OH ions or there are more hydronium ions or there are more, the hydroxide ions. So, or is the solution an acid or is the solution a base? So here we are going to be using the formula of the ion product of water, okay? Here. So it's very interesting. Let's do it this one. So here, calculation. This is a calculation based question. Calculate the hydronium ion concentration. So remember that the concentrations are always in square brackets. Square brackets are concentration, and concentration means amount, and that amount can be expressed as molarity, or in this case, okay? So let's look at, now they are saying, let's look at this question, 11.38, I'm going to just put here, or the OH ion concentration using the KW equation, okay? So let's do this problem here. Indicate whether each of the following solution is acidic, basic, or neutral. Okay, that is one type of question. And second is calculate the OH ion concentrations. calculate the or hydronium ion concentration if the following. Okay, let's do this one. 11.40, and this is page 416, page 416. Okay, so you guys are going to do all this with me now. Okay, so here calculate hydronium ion concentration. Let us say aspirin. Aspirin is given to you. This is an aspirin solution. And you need to calculate how much of the OH ions are there. Okay, so calculate the OH ion with the following. So you are given in the aspirin solution, you are given OH ions, and these OH ions are 1.8 into 10 to the power negative 11 molar. Okay, 1.8 into 10 to the power negative 11 molar. Okay, so what do you do here? You are going to have Kw is equal to concentration of the hydronium ion, H3O plus, times the concentration of OH ions. And the formula here is 1.0 into 10 to the power negative 14, okay, is equal to 1.0. So hydronium ion concentration you can find if you are given the OH ion concentration, which is 1.8 into 10 to the power negative 11. Okay, so you will have to use a calculator now, or you can do it manually. So here's the thing, that 1.0 into 10 to the power negative 14 divided by 1.8 into 10 to the power negative 11 is equal to the hydronium ion concentration. It's a simple algebraic conversion, right? Next is you're going to just do 1.0 on the calculator, divide by 1.8. That's one thing. Next thing you're going to do is whatever number you get here times 10 to the power negative 14 plus 11. So this becomes, what do you get here?
Negative 3.
Negative, no, 1. Yeah, negative 3, that's true. But what about the other one?
0.5. 5.
Okay, here it's 0.5 into 10 to the power negative 3. Everybody got it?
Yes. Yeah.
Everyone? But here's the thing, you have to convert this into scientific notation. Scientific notation. So that's back to your first and second chapter. How would you do that?
You do the initial number, which is 0.5 in this case,
Right.
and then do it 10 times whatever power.
Yeah, and you move the decimal here. So you moved it one place. So this becomes 5.0 into 10 to the power, what?
Negative 4.
Negative 4m. Always important to write the, in what context. See, when I'm asking you, I'm looking at your work, right? I'm looking at your work. I haven't yet finished the grading. So as you can see that, you know, when you write, I mean, fine, this is fine. Many of you are showing good working, but just make sure that you put the units. Don't forget those. Okay. Sometimes you think like it's a scratch word, it's understandable. No, you should follow. Okay. All right. So this is how, you know, this question is going to be, there's one question from this. Okay. So in a way we covered here balancing, we covered here titration, which is basically stoichiometry, right? And then we covered the concept regarding the molarity, right? Moles over liters. So everything, you know, comes here in this. So, and then we talked about the equilibrium, right? And then we talked about the what is it called? Finding the concentration. Now tell me one thing more. Is this equation, is this solution an acidic or a basic solution? Is it an acidic solution or is it a basic solution? So your hydronium ion concentration is, hydronium ion concentration is 5.0 into 10 to the power minus 4. And your basic was given What's that? It is given already. OH ion concentration was, what was that? 1.8 10 to the power negative 11. 1.8 into 10 to the power negative 11 molar. So which one is more? Which one is more? Is it acidic or is it basic?
I would say it's more acidic.
Yeah. Why do you say that, Josh?
Because greater value. Again, you don't want, like in scientific notations, if you have a negative power value, less
Right.
is more.
Less is more. Very good. Excellent. Excellent. So this is a bigger number in comparison to this. Okay. So, you know, this could be misleading. So this one you can go, but always pay attention to the exponents. That's, you know, where the power and the zeros, all that placement comes into play. So 10 to
Charge
the power
matters.
negative 4 is bigger than 10 to the power negative 11. Therefore, hydronium ion concentration is more than the OH ion concentration. So this type of question can be asked also. So whether the solution is acidic, yes, this solution is acidic in nature. Okay, and when we say acidic, now another question is pH. What should be the pH? More than, less than, or equal to?
Less than 7.
Less than 7. pH is less than 7. Okay, that is another, you know, we can put the pH indicator. Okay, so this can come. And what else? Yeah, so now we talked about the ions. So another question that can come is on the Ka values. You know, what are the Ka values? Basically, you know, those you can do. So what I'm covering is, it's not like I'm covering the entire test here. Some of the other, you know, questions will also come, but I'm focusing on, like, you know, main student learning outcomes, like a really big stuff. So you should really do a full-fledged review on your own, but like, yes, focus on this like as a top priority, you know, so you don't miss out, like at least, you know, doing good on the final exam. Okay. All right. So next is, obviously you need to know the names of the acids, and, you know,
Bases.
names of the bases. Yeah. So those things, basic things. Okay. So next comes the question on the equilibrium and the reaction rates. And here we are going to look at the Le Chatelier's principle. Okay. And calculating the K value. So just put it here. This is your question. This was a chapter on acids and bases. So let me just put this here in acids and bases. Titration 1. The second thing is the proton transfer reactions 2. Then comes the identifying the conjugate acid base pair 3. And then calculate. So these are the 4 main things here, right? Main is that. The rest is as theory, you should know. Okay, now we are looking at the next question, which is the equilibrium conditions. The equilibrium, reaction rates and equilibrium. Okay, so reaction rates and equilibrium. So like, I'm going from the back side. The most, like, critical pieces are always, you know, higher ones. So let's look at this. First of all, in this case, we have the Le Chatelier's principle. Okay. Okay. All right. Now let's look at this question. We have, let's see. Okay, let's do this one, 10.3, because some of the questions I'm taking not exactly from your homework, but kind of your homework questions. Okay, so this is page 392, and this is this problem 10.30. Okay, 10.30. Okay, now we have this problem. Then now we have this question or an equation, which is, okay, nitrogen as a gas reacting with 3 moles of hydrogen as a gas. And this is stuck at equilibrium. It's giving you 2 moles of NH3 as a gas, okay, and 92 kilojoules of heat. So this is the heat is. So well, first of all, what kind of reaction is this? Exothermic or endothermic?
I assume exothermic because the heat is on the product side.
Very good. And what about the rest of the students? Do you guys agree or don't agree with Joshua?
I agree.
Agree? Okay, good. Okay, this is going to be your presence also. There are 21 students in the class. Okay, good. So yeah, you know, so guys, here's the thing. Like, this is, I'm kind of warming you up so that you do good on the final exam, right? So just right now, you best, everybody should be alert and participate. Okay.
Yeah.
All of it can be covered. You know that, like everything can be covered, but very important pieces so you don't miss out. So everybody should participate. Okay, anyway, so this is when you write heat here on the product side, that means those reactions are exothermic reaction. And another way of writing the same, I can give you a problem in which the equation is written like this. Another way can also be this way: N2 as a gas plus 3 moles of hydrogen as a gas stuck at equilibrium, 2 moles of ammonia as a gas, delta H is equal to negative 92 kilojoules. So pay attention to negative for exothermic
Loss.
reactions. Yeah, exothermic reactions. Yeah, that's a good way of looking at it, loss. So for exothermic reactions, the value of delta H is negative. I mean, you know, if you put it on a graph, yeah, you're going to find that the heat of the formation of the products minus the heat of the formation of the reactant. So the heat of formation of the products is lower. The heat of formation of the reactants is higher. So smaller number minus the big number gives you a negative number. So that's one way, but just apparently the way to like loss is exothermic. Good. So, all right. So now we are going to, now the question here is asking you, let's see. Okay, for each of the following changes of the equilibrium, indicate whether the equilibrium shifts in the direction of the products, whether the equilibrium is going to shift, whether the shift is going to be in the direction of the products, reactants, or it doesn't change. So that's the simple question they're asking. So what? So if you, so first part is A part, which is they are saying remove the nitrogen. So if you remove nitrogen, what happens? What is the direction of the equilibrium? Forward, backward? You removed the nitrogen. You're removing nitrogen. This guy removed. Then what happens? Does it move forward? Does it move backward? Remember, it's the system is always going to work in the opposite direction. In the opposite direction means that you removed nitrogen, now the system wants to produce more nitrogen. So in that case, it moves in the backward direction. So if you, so it moves backward, and another way of saying it, that it moves in the direction of the reactant. So it will want to produce more reactants. So this is so the shift is going to be towards the reactant side, shifts towards right. So the equilibrium shifts to, we're going to put it like that. Okay, next is, if you, our next question is decreasing the temperature. So decrease temperature. Remember, now in this case, pay attention to the situation where the heat is a part of a product. Heat is a product. So now you remove this product, 92 kilojoules of heat. Now the system is moving which direction? Yeah. You removed the heat which is acting as a product. It moves forward. Very good. Because now it wants to produce more heat. You removed the heat. Now it wants to produce more heat. So it moves towards the product side. Okay, very good. Next is you add more add more ammonia, NH3, add more ammonia. So now you are adding a large, from outside, you bring from your side, you add more ammonia into the system. Now which direction is it moving? Yeah. It is moving, large excess of ammonia. What about the rest of the students? I see a response from Joshua. What about the rest of the students? It's moving backwards. Yeah, large excess of ammonia. So the system is going to move in the direction which is opposite of where you're applying the change. Okay, so it moves backward. So in other words, now it's going to produce lots of reactants. In other words, you know, our N2 and H2 will be produced. Okay, very good. Next is adding more hydrogen. Now you added from your side more hydrogen. More hydrogen, what happens? Large excess of hydrogen is now there. Now the system moves. Large excess of hydrogen. Yes, that large excess of hydrogen, it consumes all of the nitrogen. And what has it produced then? Forward. It produces ammonia. So now it's forward. So you see, wherever you kind of have to like visualize this also. So when there's large amount of hydrogen, it will quickly consume all of the nitrogen, and then it is moving. That means in the forward direction, it is actually producing the ammonia, a lot of ammonia. So it's products, lots of products, okay? The E, the last part E, increasing the volume, increase the volume. Now which side is it going to move? Remember that volume and the number of moles go hand in hand. Number of moles directly proportional to the volume of the container, volume of the gases. So it is just going to move whichever direction there are more moles. So volume, so number of moles increase, volumes increase, number of moles decrease, volume decrease. So in other words, if you decrease the volume, the reaction is going to move in the direction wherever there are less moles. If you increase the volume, the reaction moves. So basically we are looking at the reaction, right? Equilibrium. It's going to produce in the direction where there are more moles. So now here, let's look at this. So here we have 1 mole of nitrogen plus 3. So total moles are how many? On the reactant side, how many moles do you see on the
4.
reactant side? 4. And how many moles on the product side?
2.
2. Okay, so here's the thing. 4 moles total. Total 4 moles on
Reactant side.
reactant side, and then for total 4 moles on the reactant side, and a total of 2 moles on product side. So now if you increase the volume increase the volume, then the number of moles, the reaction is going to move towards the reactant side. Okay, so reaction moves towards the reactant side where there are more moles. Reaction moves towards reactants side. Okay, more moles. But on the other hand, if you decrease the volume, let me just write this down because this can be a little bit confusing sometimes. So this is one part here, some part, and like here is if you decrease the volume, then what happens?
It would go towards the product side because it would shift toward, because more collisions would occur.
Right. So decrease the volume. That means that the let me put this here. Volume has decreased. Then the number of moles, reaction is going to move towards the product side. Okay, product side reaction reaction moves towards the product side. Okay, so that there are less moles there. Here there were more moles, 4 moles, and here there were only 2 moles. All right, guys, clear? Everyone clear? So this type, again, Le Chatelier's principle, this is on the test. This is an important concept, okay? So just make sure that you don't get confused. Sometimes the left and right, too much left and right. Sometimes I also get like, oh, no, yeah, it can be confusing. So if you're less stressed out, relax, and then just visualize it, then it can be, then you can do it, okay? All right. All right, next question is going to be on the on using the Kc value to find the the concentration, the equilibrium concentration. Okay, let's do this one. Okay, let's do this one. The using the equilibrium constant. Number 3. So equilibrium, EQUILIBRIUM, equilibrium constant, KEQ or KC, it's the same thing, okay? All right, so now in this equation, let's do this question, 10.28, and this is page 386, page 386, okay? In page 386, you're given this problem, 3 moles of hydrogen, okay, as a gas, reacting with 1 mole of nitrogen as a gas, and this is again at equilibrium giving you 2 moles of NH3. Okay, and again, this is a gas. Now the question is the Kc for the following reaction. The Kc value is already given, and that is 1.7 into 10 to the power 2. Okay, if the equilibrium mixture contains, now the value of the concentration of hydrogen, this is given. Hydrogen is equal to 0.18 molar. And the nitrogen is 0.020 m. Okay, what is the molar concentration? NH3. What is the molar concentration of ammonia? So a little bit of math here, but let's see how we can do this. Sorry. Okay, here we are doing this. So important, see, guys, you're going to be graded on showing all the work. That is important, okay? So here we are doing this. In this case, we need to find the concentration of ammonia. So first of all, the value of KEQ is equal to the concentration of the product is going to be on the top, which is the product in this case is ammonia, NH3, and that is raised to the power 2. Right, and here you have H2 raised to the power 3 multiplied by concentration of nitrogen raised to the power 1, which is just 1. So next you are going to write down here for the ammonia we need to find. So NH3 raised to the power 2, just leave it as it is, over, and here I'm going to write down Kc value, 1.7 into 10 to the power 2 is equal to, here you have hydrogen is 0.18, hydrogen raised to the power 3, okay, into nitrogen is 0.020, and that's raised to the power 1 means it is what it is. Next is the algebraic conversion, and that is 1.7 into 10 to the power 2. This is one set, right? Multiply by, you have 0.18, right? Raised to the power 3, right? Multiply by 0.020, 0.020 is equal to the concentration of NH3 raised to the power 2. Okay, so do this math. First do this math. Do the math and tell me what you get. What do you get, guys? So 1.7. Oh, wait. So this is 0.18 times 0.18 times 0.18. And you get 0.005832 times 0.020, and that is 0.00. Just do this 1.7 into 10 to the power 2, and you get here 1.7 into 10 to the power 2 times 0.000116664. All right, this times 1.7. So this comes out to 0.019. H3 raised to the power 2. Okay. What? Yeah, 19828. Yeah. Let me just bring in all of this number. So right now we are not applying any, rules regarding the significant figures, but 0, 0, 19821982888. Okay, is equal to NH3 raised to the power 2, or in other words 0.01982888 is equal to NH3. Do this. Don't forget this part. Don't forget remember this is ammonia. This is 2. This comes here. And so if we are doing this, then we need to do the, bring this also in the algebraic conversion. And so it shows like that. So what do you get here? 0.1408, 0.140808, 14, yeah, 14. So, okay. So now we can do the significant figures. Just, we can, I didn't want, because the thing is that anytime you're doing in between, you don't round up or round down. Okay. So what about the rest of the students? Are you guys getting the same answer, or are you getting anything different? Yeah.
Yeah, he's right.
Point. Everyone got it? Same? Everybody? Okay, good.
Heck
So
yeah, right?
you're the only, now let's just look at it a little bit from the significant perspective also, significant figures, just in case. So this is 2 significant figures. Okay, this is 2 significant figures. And this is also these two significant figures. Okay, so your answer, from here, this is, I like to just use it as many numbers, before first do it, because the thing is you don't round up and round down in the middle. Okay, so let's look at this. So this is again, in this case, 2 significant figures. Here, your answer should be 2 significant figures. But That's what I'm saying, you know, if you, so if you, when you multiply, oh, this gives you only here, 0.58, and this one is just like that. So again, two significant figures and two significant figures. And so this should be this, but like I'm saying, that's why I'm scared, don't round up. So just leave whatever numbers you get, you know, in the middle and kind of go from the, then get it in the final answer. So here again, two significant figures. And ideally this is two significant figures. So with that said, this should be 0.00012, but we just leave it as it is in the calculations. So once we get this, ideally your answer should be two significant figures. So here is this thing. Once you do the square root, you know, then this comes out to be this thing. So just bring it as the answer to be 0.14, you know, zero, this zero, just leave it like that, molar. Okay. So leave the answer like that. So again, like I'm saying, if we start bringing in the significant figure rules in between here, then this gets, then this would be 0.0, you know, 20, or it's to avoid. So I'm going to say avoid rounding up in between the steps. So just keep this in final answer that you started off initially, just keep this as your initial. This was your initial. So initially we started off with two significant figures, therefore your final answer should also be two significant figures. So in the middle, like I showed you, like, you know, we don't bring that. It's going to create a lot of, you know, errors then, okay? All right, so that is your molarity for this one. So, you know, I mean, you should know what numbers to punch in on your calculator in order to get the square root thing working, you know, this problem, the last step. But if you have not done that, then just make sure you know it, how to do it, okay? So, but anyways, I'm telling you this question based on where the concentrations are given to you. You asked to find the value of K, and that is an important question, okay? Equilibriums. And since this question involves the writing of the equilibrium equation, so you know that is what it is. And then just know the theory, you know, what is activation energy, what is exothermic reaction, what is endothermic reaction, what is a catalyzed reaction, what is uncatalyzed reaction, and like what are the factors that affect the speed of a reaction or the rate of a reaction. Okay. So that's like all that is important. Okay, now the last is this chapter, which is very important, and that is the chapter on solutions. Okay, so in the solutions, and again, you know, guys, it's not possible to cover everything, like I'm saying, but you should, these are like the very important pieces, but you should go back and again review, you know, review other pieces, other small, you know, theoretical questions or easy questions or, you know, simple questions also from the lecture notes. Even if you just at this point, I would say do this thing, go back and just look at the lecture notes, because all the lecture notes we covered the questions from the book only, right? So that would be like kind of a good review also for you. So okay, so we covered here reaction rates and equilibrium, this chapter. And in this chapter, this is important, and this is important, very important. And the rest of the stuff, obviously, you know, you guys should do. Next comes the solutions. And okay, solutions, very important chapter, very important, like a lot of things in this chapter. Okay, so this one and then the stoichiometry chapter, again, very important, both of them. Okay, let's look at this. What time is it? Okay, change. So here, you know, the change in boiling point and melting point. I'm going to give that one definitely, because, you know, it's the way it is shown in your book. There is obviously not very clear. And what you will do is you are going to, yeah, let's do this one. Okay. First is the the, what is this called, the colligative properties. So colligative properties of the solutions. Colligative properties are the elevation in boiling points, you know, depression in freezing point. And so these are the two main important ones on which are based on the formula.
You okay?
Yeah, I'm fine. Which is based on the formula, not very clearly written in your book. So best is you write down and again review the whole of it from the lecture notes. But here is a question: calculate the boiling point. So this is, we are looking at this problem, 9.76, and this is page 360, page 360. Okay, so here you will have calculate the boiling point. So we need to calculate the boiling point. Calculate the boiling point of each of the following solution. NaNO3, yeah. So here you are given this point C. I'm going to do point A, and then we're going to do point C also. So point A is 2.12 moles of glucose. Now, anytime, now glucose, yeah, we will give you glucose, but we will also give you the formula for glucose, which is C6H12O6. Okay, a non-electrolyte. Let me turn off this thing, 1 minute. Okay. All right, now we have, this is a non-electrolyte. So remember that non-electrolyte. Electrolytes are those that ionize in the solution, and non-electrolytes will not ionize in the solution. So for the non-electrolytes, the value of I is always going to be 1, even though they don't ionize, but that's what we give them, okay? So the question is, what is the boiling point of a glucose solution? 2.12 moles are given, is added to 1 kilogram of water. So the solvent here is 1 kilogram. Okay, so the formula, like I said, the one that is not given in your book and you need to know it or write it or put it in on your handout. So delta TB is equal to I times, what is it, KB times the molality. Remember, M dash is molality, not molarity. This is molality. Okay, and what is molarity? Molality. What is the meaning of molality? Do you remember? Formula? Formula for molality?
Yeah.
Moles of the solute over kilograms of the solvent. So moles of solute over the kilograms of solvent. Moles of solute over the kilograms of solvent. Okay, so now what do you put here? KB, okay, yeah, you guys will be given the value of KB, which is equal to 0.52 degrees Celsius, kilograms per mole, kilograms per mole, kilograms of solvent per mole of solute. Okay, so delta TB is a change, final minus initial. So let's do this now. Start plugging in the numbers now. So delta TB is equal to, the value of I is equal to 1, right? Times the value of KB is 0.52 degrees Celsius, kilograms per mole, right? Times the moles of the solute. So what is given to you here, moles of the solute? 2.12 moles of the solute, molality, over how much is the kilograms of solvent? 1 kilograms of solvent, and the solvent is water. Okay, clear? So this whole piece right here is molality. Either they will just give you the value of molality, or this is how you can, plug in the number. So this is the M dash. Okay, now you calculate this. 1 times 0.52. Now do this math. Do the math. 0.52 times 2.12 Very good. So this becomes 1.1024. And once again, you know, here we are going to look at the, let's get to significant figure situation. So this one we omit the one. So this is 2 significant figures. And this guy right here is 3 significant figures. So the final answer should have 2 significant figures. So 1.1. Okay, so you can, it's safe to write in this case that the value of delta TB is equal to
1.1
degrees Celsius. And if you look at it, how did you get degrees Celsius? Look at it here. Kilograms and kilograms cancel out, moles and moles cancel out, and all you're left with is the unit for the degrees. Okay, so that is the change in volume, but the question is asking what is the final. So delta TB is equal to T final minus T initial. Now always remember that the boiling point of water is equal to 100 degrees Celsius for water, pure water. And when you add glucose to it, 2.12 moles, and you can convert that to grams, so you know how many grams of glucose you added. So that brings the change in volume, change in the boiling point by 1.1 degrees Celsius. So that means that we need to find T final. We know that the change was 1.1 degrees Celsius and the T initial was 100 degrees Celsius. So when you do the math, you get T final is 101.1 degree Celsius. So that is the new boiling point after you added the glucose to it. All right. Now same thing. Now there's another question here. This one was part A. This is part A of this problem. This was A, as you look at it. Then the part D is talking about, now I'm not going to repeat the whole thing. It's the same thing. The only thing is Na, NO3. So it is the value of I. So in this case, what is the value of I? Tell me, you guys tell me. It's not going to be 1. This is an electrolyte. Electrolytes are
less than 1.
Electrolytes are like, you know, ionic compounds that solubilize in water, that ionize in water. So what is the value of I? What are the ions? Yes. How many ions are there? 2. You have sodium ion, and then you have 1 nitrate ion. Remember that? Let me do one more example. Suppose you have Mg, wait 1 second, OH whole twice. What is the value of I? How many ions are there, total ions that are going to be released? 3, very good. So this is 1 magnesium ion, and 2 OH ions. So I is equal to 3. Okay, let's do one more. Al2CO3 whole thrice. What is the value of I? Yes. Not 4. It's not 4. Al2CO3 whole thrice. How can it be 4? So there are 2 aluminum ions plus 3 charge, and there are 3 carbonate ions minus 2 charge. So what is the total? How many ions? 5 very good. So you got it. So the value of I is equal to the total ions that are released. Okay, guys. So this is very important. Okay. So same is the case with the freezing point. So just keep this in mind that boiling point is 100, freezing point is 0 for water, and we are going to give you the value of the Kb and the Kf values. So let's move on to the next one. So this was the colligative properties. This is important. This was 1. So again, test question, and you guys need to focus on you know, practicing these questions. Okay, I might give freezing, not boiling, but you know, just pay attention that you need to get the final. Okay, next is the question that relates to dilution. Now this is the one where, sorry, this is the one where students make a lot of mistakes for the dilution problem right here. I'm going to finish the solutions and then I'll give you a little break. I know it's a lot today. We're trying to cover a lot, but I'll see, or maybe no break. I don't know. We'll see. Quickly, let's try to finish this. Okay, for that now, guys, a lot of students make mistake. First of all, remember that dilution is not a chemical reaction. So I don't know how many times I have emphasized this, but let me just make this like really, really thick. I hope this is not, oh, sorry. Okay. So this is a physical process only. No new product formed. I'm making it thick, you know, so that you kind of remember it. Okay, no new product is formed. And this is simply adding water. That's all it is. Simply adding water. It's not even like you're bringing in another chemical. No, simply adding water to to some solution. So that's what it is. Okay. So don't forget that. Okay, guys. Many of you make, I don't know, use the dilution formula for whatever different types of other things. So here, M1 V1 is equal to M2 V2. Okay, this is one. It is also in your book, the way it's stated is C1 V1 is equal to C2 V2. So it's the same thing. Okay, both of them are the same. Both of them are the same. On one side is a higher concentration. The value of M is large. The value of volume is going to be lower. And here we are trying to make a solution which is less concentrated, and we are making a large excess of it. So volume is large. Okay. Now let us do one problem here. So determine the final volume in milliliters for each of the following. Okay, here is you are given, yeah, and it is also the same solution. This is also the same substance. So it's not even like you're bringing in something else from outside. Same substance plus water, that's all. And so it's a physical change. It's a physical change. Okay, all right, now here's what, let's look at this 9.66 problem. And this is 9.66 and this is on page 351. Page 351. Okay, here you are given, okay, let me first write down here. NaOH solution, we are talking about NaOH. So write down NaOH. 1 molar. So molarity is given, 1.0 molar. Solution is prepared. Okay, so that is M2. So just keep this in mind that this is prepared and this one is given. So this is another way of looking at it, okay? So this is M2, this is M2, or in other words, this is prepared. All right, molar solution is M2 and not here, sorry. This is M, just plain M. Okay, a 1 molar NaOH solution prepared from 50 ml volume V2 is 50.0 milliliters. Okay, of 12 molar NaOH. So sorry, this is the V1 and this is M1 from 12 molar NaOH. Okay, A 1 molar NaOH solution prepared from 50 milliliters of 10 molar NaOH to determine the final volume. So what is the final volume? So keep this also another thing, that this is the final and this is the given initial. So you take out a little bit from the higher concentration and you add water to it to make it a lower concentration.
600.
Okay, and then that gives you the less concentrated solution.
600 milliliters.
So important thing to understand here is that because molarity, right? Molarity is moles over volume in liters. So you have to change this, convert this to liters, and molarity is obviously molarity. So if you have this molarity, convert this milliliters to liters. That's the first step always. So let's convert that. 50.0 milliliters times 1 liter over 1000 milliliters. And that gives you 0.050 liters. That's one thing. Now, all you need to do is just plug in the numbers. M1 V1 is equal to M2 V2. Okay, and so you are getting 12. Oh wait, 1 second. I'm putting it wrong here. Okay, so here is your 12 molar times 0.050 liters. So this is what you have taken out from a more concentrated solution to give you 1.0 molar solution times, we need to find what is the volume of this in liters, okay? And so then comes 12 m times 0.050 liters over 1.0 m is equal to V2. So this is going to be in liters. So what do you get here? Do the calculations, guys. Okay. 0.6, very good. So this is 0.60, okay? Or 600 milliliters. 600 milliliters of volume. So this solution is going to be, so is either in milliliters one of your choices, or so. So this is one thing. Okay, so this is going to be on the test. Next thing, now stoichiometry. This is so important, guys. So important. Stoichiometry of the reactions. So colligative properties, dilution formula, because this dilution formula, again, remember that this is something, if you were to work as a teaching assistant in chemistry labs or even in a biology labs, all they do is make these solutions there for the, students. So this is going to be your job. This is going to be your job. So you should know how to use this formula. Otherwise, it's all messed up, okay? All right? Clear, guys? Okay, next is the solution stoichiometry. Solution stoichiometry. Okay, solution stoichiometry. Now, very important. Here you're going to use the molarity to calculate the volume in a reaction solutions where the actual reactions are happening here. So in this case, this is a reaction. Okay, now let's do one problem here. And so just like the titration, as I told you, right? Just like the titration. Let's get one problem here. Answer the following. How many milliliters of, so okay. I'm also now covering the stoichiometry, like I said. This is the student learning outcome, SLO. Very important. So you just nail it down if you're still struggling with it, because see, here's the thing. students sometimes who are going in the nursing field, they think that they just need chemistry to meet a prerequisite and that will be done. That's not the case. You know, chemistry, you need, because all the chemicals, the medicines are chemicals, right? And so when you go in the workplace, you will be doing these solutions. So you'll be making solutions. You're also going to like all kinds of things. You will be using chemistry heavily in the workplace. So best is to nail down how to do these right. So otherwise you'll have to learn it in the workplace and you can't afford to make mistakes there. It's okay to mistake here, okay? So you learn more. So I think don't be afraid. Just try to apply yourself and see if you can nail this down. Okay. So here you are given calcium. This is a problem 9.52. 9.52, and this is page 348. Page 348. Okay. So here you are given calcium carbonate. Calcium carbonate is a solid, and in that calcium carbonate, HCl is being added. HCl is aqueous. So, or in other words, this could be, a reaction that is happening in a human body. HCl acidic, right, in a human body, and you have this stomach acidity. And now, how much of calcium carbonate should be given? Like if calcium carbonate was one of the, active ingredients in a medication, or if it's not sodium carbonate, it's not calcium carbonate, it could be something else. So what is that active ingredient that is going to neutralize the HCl? So we do these type of problems. We do these type of like labs, experiments in the lab. So in the real world, you can get a feel for it. But anyway, so here's this calcium carbonate with HCl, gives you carbon dioxide as a gas and water, H2O, as a liquid, and calcium chloride, CaCl2. Okay, aqueous. All right. How many? Question here is part A. How many milliliters of 0. Find the volume of 0.200 m HCl solution will react with 8.25 grams of calcium carbonate? Okay, so you are given 8.25 grams of calcium carbonate and you're given the molarity of HCl and you need to find the volume, how many milliliters of volume of HCl here, HCl. Okay, so same stoichiometry, check the balancing. Yes, the balancing is fine. 2 HCl, two hydrogens, 2 chlorines, 1 calcium, 3 carbons, 3 oxygens, and 1 carbon. Okay, it's all balanced. Good. Now, first thing you're going to do is that you are going to, so we are basically looking at
Right.
the relationship of calcium carbonate and HCl, right? So
Yeah.
you are given 8.25 grams of calcium carbonate. What is the first thing you're going to do?
Find the molarity of that.
No, moles.
Moles of that. Yeah.
Very good. Yeah, find the moles of calcium carbonate, right?
Yeah.
And how to do that? You
calculate the mass of.
very good. The molar mass. So guys, you guys do it. Come on, you guys do it. Molar mass.
Got it. I'm getting the table.
Yeah. So pretty much, it's from your previous chapter, like 7, kind of all those things are going to come together in this. I don't have to do like a major review in chapter 7. It's just the limiting reactants now, but you can be tested this way. Okay, molar mass. Calculate the molar mass. CaCO3. So there's 1 calcium, 1 carbon.
Calcium, that would be, let's see, 40. So 40 plus 12 and plus about 16. So 48. Oh, sorry. 48 plus 12 plus.
Right. 40. Okay, 100 grams per mole. Okay, so
So
do this 8.
8.25 divided by 100 equals 0.08. Two grams.
How much is it?
0.082 grams. 3 places?
Yeah. No, write down 8.25 divided by 100.
Yeah.
How much is that?
0.082.
Very good. Point 0.0825 moles.
Wait, I thought we were cutting it based on significant figures.
Yeah, you could do that. 3 and 3. So we need 3, right?
Yeah.
That is, there are 3 significant figures. 3.
Yeah, sorry.
And then this one also is in a way 3, although this could be like not very important, but the 8.25, this is what we will do. So that is why you need this whole thing. Okay.
Oh, yeah, sorry. Oh, God, why did I think that? For some reason, I thought if a 0 is tied to the placing of it. Oh, God. Need to stop remembering. 0 are not significant figures. 0 are not significant figures.
Yeah, you know what? Here's the thing. Anytime you're confused, anytime that happens and you get confused, best is to focus on how does it look like in those numbers where there is a decimal.
Yeah.
So in this computation, 8.25 is like kind of like a driving force in deciding what should be the significant figures in the final. Because yeah, the exact numbers, the significant figures can vary. For 100, it could be, 2, it could be 1, those type of things. But so
Yeah.
it's kind of not very conclusive. But always the decimal, anytime a number is there with the decimal point, go by that. Okay?
Got it.
Right. So now we have the modes. Next, what are we doing here? So what are we doing here next?
We need to figure out the ratio of each type of element.
To 5 moles of calcium carbonate.
Yeah.
Okay. And then next is you are going to look at now here we are looking at the calcium carbonate moles. Convert that to the moles of HCl, right? Using the mole to mole ratio. So moles of calcium carbonate converted to moles of calcium, moles of this thing using the mole to mole ratio.
Got it.
So now, how many moles of HCl are there? 2. How many are calcium carbonate? 1. So 2 to 1 ratio. So 2 moles of HCl in this reaction and 1 mole of calcium carbonate. And what do you get here?
0.165.
0.165. Very good. Moles of HCl. So now we have the moles of HCl. Next is we need to find the volume of HCl. And what is given to us? The molarity of HCl. So here's the third step is molarity is given, what is that? 0.200 m. We need to find the volume in liters, and I think the volume in milliliters. Later we will convert to milliliters. That's what they want. And then we are given the moles. We calculated the moles of HCl is 0.165. 165 moles. Okay. So molarity is equal to moles over volume in liters. Moles times volume in liter is equal to, no, what was it? We need to find the volume, sorry. So volume in liters is equal to moles over the molarity. So just plug in the numbers. Volume in liters is equal to The moles is 0.165 moles over the molarity is 0.200 m. What do you get here?
Second answer divided by 0.2 would be 0.825. Oh, do we have to convert that to liters now?
Yeah. 0.825? No. You sure?
Oh, 0.8.
0.165 divided by 0.2. Oh yeah, 0.825. Yeah, you're right about that. Mistake here. 0.825 liters. And next question is the last part, which is they want the liters to convert to milliliters. So you have 0.825 liters times 1000 milliliters over 1 liter. And what do you get here?
Uh, 825 liters. Milliliters. Milliliters. Oh, God.
It's okay. Well done. Okay, everybody got it? Okay.
Yeah.
So I see like just a few people are participating. What about the rest of the class?
Oh, good.
It's been better, right? If you guys do this is like that I'm just telling you. This is your important student learning. Oh, there is going to be a question on this type of question. Just keep this in mind that the whole stoichiometry is important. So all these moles and volumes and all that. So just make sure that you do that. All right. Next is I can only do so much. We already did titration. This one we did. The next thing that you are going to just look at yourself, and I'm not going to do those questions now, but like I said, I'm going to just only pick in the important ones. So in the solutions chapter 1, 2, 3, now comes the fourth part, which is you guys are going to look at it on your own, look at it mass by mass person problems. They're going to be, they can be, I'm not saying I haven't made the exam yet, but I'm just telling you that volume by volume percent. Okay, this is the other, solution, reaction stoichiometry, sorry, the concentration of the solutions. And then comes the mass by volume percent, look into those problems and look at the molarity questions where you are given, the moles and the volume in liters. Okay, so just pay attention to, so this is the moles of the solute and this is the volume of the solution and this is in liters always. That is why we have to do those conversions. Okay, so all these interconversions of these conversions. So just pay attention to another thing is if you are given the grams, you always need to first convert to moles and then you can use it in this formula. Okay, so again, important stuff. You will need to know this and you will get that. Now another thing is the ionizing. This is also important. Ionization. Okay, writing the ionic and the net ionic. I know it is a little bit hard, but writing the net ionic and the ionic equation. So you also need to know the ionic equation, net ionic equation, and you also need to know the solubility rules. At least know how to use them from the table. Okay, very important. Okay, so here let's do determine whether the solid from the solution contain the following compounds. Yeah, So write the ionic kinetic. Let's just do this. 9.32, one problem here. 9.32, and this is page number 339. And in this 339 page number, okay, you are given K2SO4, no, yeah, PbNO3 and sodium carbonate. And they are asking you identify the product. So here, okay, balance. So first of all, identify the products. So these are the things. Products, you should know how to identify the products when two things are reacting. Next is identify the solubility. Okay, whether it's soluble or insoluble. Okay, next is you should know how to balance that equation. Okay, next is you should know how to ionize that equation, write the ionic, that's the total ionic, and then you should know write the net ionic. So all this is like important stuff. Okay, so let's do this. You are given lead nitrate, PbNO3 whole twice, plus sodium carbonate, plus I'm going to PbNO3 whole twice, plus sodium carbonate, Na2CO3, and this gives you Na2CO3. Okay, and this gives you, now what are the products? So that's a question that can be asked. Okay, so here outer, inner, inner. So here is your outer. Lead is going to combine with the carbonate. So always it's very important that you know the polyatomic
So
ions. So by this time you should know it. I already asked you to do the memorization quiz, right? Remember the memorization quiz? Remember? Yeah. I asked you to memorize all the symbols, polyatomic ions, charges.
yeah.
You should know by this time. Okay, charges and polyatomic ions, and then the symbols. At least you know that. Very important. Okay. So if you have forgotten, just go back and review. And I'm going to still emphasize this. You need to memorize this. So important. Okay.
So lead would be 2, carbon
Right. So now
nitrate,
we have,
-2 pounds.
okay. So here you will have the lead,
2 charge.
carbonate, outer, inner, inner. Remember? And then here you have the nitrate.
So lead carbonate would be insoluble.
Oh, now you have lead carbonate, PbCO2, and the next is sodium nitrate, NaNO2. So you should know the charge on nitrate, charge on carbonate, and why did I not put like, why did it just PbCO3? Why not Pb like 5CO3 or whatever? So those things,
Because the charges are balanced.
yeah, balancing the charges. So here you have, now so let's first balance it. So we have lead carbonate. So lead, one lead here, there's one lead on the other side. Nitrates are 2 on one side, nitrates is only 1. So if you put 2 here, this applies to sodium and this applies to nitrate. Okay, so sodium is balanced 2, and then nitrate is also balanced, and carbonate is just 1. So that balances this. Clear? Next, identify the solubility. Solubility. Now, what is the solubility? Look at the solubility table.
Solubility is if it breaks down in water or not.
Right, very good.
And that can be determined using a solubility chart. And for PbNO, that would be insoluble.
PbNO3.
I mean, Pb carbonate.
Yeah, because all carbonates are insoluble. So this is going to be S. So remember that S stands for the solid. Everyone. Okay.
Yeah, wait, not all carbonates. I think a few are.
Group 1A. If you combine a carbonate to group 1A elements, yeah, or group 1A or ammonia, when they combine with any carbonate, soluble. Yeah, soluble. So it will be aqueous. Any others are insoluble, solid. So if you look in the table, lead and all carbonates, solid. All carbonates are insoluble. Yeah, like a solid. Okay. So what about lead nitrate though? Soluble or insoluble? Again, this table is in your handout. So you guys need to look at that, access that information from there. Yes, nitrate, soluble, insoluble. Yeah, soluble. All nitrates are soluble, so aqueous. Good. What about sodium carbonate? Soluble, insoluble. Yeah.
That would be soluble, unlike.
What about the rest of the class, guys? Sodium carbonate.
Yeah. Wait, that's insol. Oh, sorry, solid, not insoluble. Oh God, why am I saying that?
Soluble because group 1A, right? All group 1A soluble. Okay. What about sodium nitrate on the other side? Sodium nitrate, the rest of the students, aqueous, solid. Okay. So we have this thing here is now we identify. So this is the next second type of question on solubility. Okay. Very important, all these things. So you should know the solubility rules, and if you're not, then you should know how to access it in the handout and apply them and look at the solubility. So there are going to be questions on solubility. Okay, anyway, so now next we are just going to do the ionizing. So here we have one lead. What should be the charge on lead?
Uh,
Come on, guys, tell me the charge on lead.
positive 2.
Why positive 2?
Because lead has 2 valence electrons that need to be extracted in order to complete the octet rule in that case.
Okay, for the lead, the octet rule, okay, we can leave that for now. It's much more. So here, just looking at the formula.
Yeah.
See, this 2 is coming from somewhere. This 2. Where is this 2 coming from? This 2 right here. This 2, the yellow one I made just now. It's coming from top of lead. When you write the formulas, that's where it comes from. So two leads plus 2 state and 2 nitrates, each minus 1 state. Okay, that's how they balance each other out. Okay, so this one is aqueous and this one is also aqueous. Both of them soluble in water. Okay, plus, this is plus. Then you have 2 sodiums, Na plus 1. Remember? And then you have 1 carbonate, but carbonate will have 2 negative charges. So you see that this 2 right here is coming from top of carbonate when you write the formula. And this 2 right here is coming from top of lead when you write the formula. Okay. So this is like a lot of details here, but it kind of, you guys know it, because if you can balance the equation, then it's just you have to, like, same thing, just a little difference in perception. So 2 sodiums, aqueous, and 1 carbonate. And this is giving you do not ionize the solid, PbCO3 as a solid, okay, plus now you have 2 sodium ions plus aqueous plus 2 nitrate ions, negative 1 charge aqueous. Okay. So just keep this in mind. Just think that anytime you have a precipitate, that is why it is existing as a solid. So do not ionize this part. That's where we see when we look at your multiple choice answers, we on purpose give a precipitate and we ionize it and see if you will choose it. If you do, you don't get the points. Anyways, so now we have the spectator ions. Which are spectator ions? Spectator ions are the ones that do not show change in state. Okay, so which ones are those do you see here? Sodium ions
Sodium.
and nitrate ions. But how many? How many sodium?
2 nitrogens. I mean sodium, sorry. Oh God. And 2 nitrates.
Yeah, so these are, and which ones are is your net anic equation? Net anic is lead plus 2 state aqueous reacting with
Plus
carbonate
2.
minus 2 state aqueous, and this gives you PbCO3 as a solid. All right,
Good.
here guys. So there's
Yeah.
a lot of details in this. Kind of you might know it, but you just don't like, you know. So just I would just highly recommend review all the lecture notes, just kind of go through them. So because there are going to be questions from them, you know, we'll say, okay, identify whether this is a polar, non-polar solution, you know, so those things. Okay, next is your chapter on the gas laws. Now, gas laws, again, important is the reaction stoichiometry, gas stoichiometry, which is the same thing, you know. So I'm not going to repeat all of it, but I'm going to just write down here what all you need for the gas laws. So gas laws. So here you will be needing the reaction in which stoichiometry. So the only difference here is just like, you know, we did it earlier for the HCl, the same thing. It's going to be reaction stoichiometry. The only thing is a gas is being produced. That is all. So for the gas, again, you know, how many moles of hydrogen gas are produced? I mean, you guys are like, you know, in Chem 1A, we use a little bit more intense. You know, we go like 2-3 gas laws in one, no problem, those things. So anyways, so reaction stoichiometry, in this case, the gas is being evolved and you need to find out how many moles or what is the volume of that gas or what is those things. So we've done that earlier. We've done that. If you guys, yeah, let's do one problem here so that you guys are not lost, because there is going to be a test on this again. Stoichiometry, all of them, test. Okay, now I'm going to do one problem here. Potassium decomposes to potassium nitrate and oxygen produce decomposition. Okay, here 8.56 problem, and this is page 312. Okay, now we have here potassium nitrate. So, okay, 2 moles of KNO3, 2 moles of KNO3, which is a solid, is being heated, right? And it is giving you K, so it's a decomposition reaction. It is giving you KNO2, which is also a solid, and it liberates oxygen as a gas. Okay, so now the question is, potassium nitrate decomposes to potassium nitrite and oxygen. What volume in liters? So volume in liters, what volume in liters of oxygen can be produced from the decomposition of 50 grams of potassium nitrate? So you are taking 50 grams of potassium nitrate and you are trying to find the volume of oxygen gas. This is the oxygen gas, volume of oxygen gas at 35 degrees Celsius. So that's the temperature, and atmosphere pressure is 1.19 atmosphere. Okay, pressure is 1.19 atmosphere. Okay, yeah, so here, let's see, let's do this one. Okay, potassium nitrate, KNO3 to oxygen. So here's your roadmap. First, KNO3, find the moles. Okay, Next is you are going to take the moles of KNO3, and convert those moles of KNO3 to the moles of oxygen, again using the stoichiometry. Then you are going to, now we have the moles of oxygen, right? And you just plug those in into PV is equal to N or T. And since we need to find the volume, volume is equal to N or T over P. So if you look at it, we are given the pressure in atmosphere. So the value of R is 0.08206 liter atmosphere per mole K. Okay. All right. So temperature you are given is 35 degrees Celsius. So make sure that you convert that to Kelvin. So 35 plus 273. 273 plus 35.
That would be
and that is giving you
308.
Kelvin. Very good. And then you are given the pressure already in atmosphere, no need to change it. And that this is what it is. So let's find the value of N first. Okay, and that is for oxygen. And so we are just going back here. So now you are going to take 50 grams of KNO3. So first is KNO3, the molar mass. So potassium is 39.10. K is equal to 39.10. Okay, nitrogen is 14.01, and oxygens, and there are 3 of oxygens, that is 3 times 16. So here we have 39 plus 14 plus 48. We get
101.
10, 101 grams per mole. Very good. So let's take 50 grams of KNO3 and times 1 mole over 101 grams of KNO3.
0.5 moles.
How much is that?
0.5 moles about.
0.50 moles of KNO3. Okay, KNO3. Next is you're going to go back to the convert that moles of KNO3 to the moles of oxygen. So how do you do that? You take 0.50 moles of KNO3, moles KNO3 times the, now you look at it here, 2 to 1 ratio. 2 to 1 ratio. 2 to 1 ratio. So 1
Answer
mole
times
of 2 moles of KNO3.
divided by 2 would equal 0.25.
Moles of oxygen. Okay, so now the third thing is just plug it into the numbers. So volume is equal to N or T over P. N is 0.25 moles times 0.08206 liter atmosphere per mole K times, what was the temperature? 308 K. Okay, over pressure was 1.19 atmosphere. Okay, so now you have atmosphere and atmosphere cancel. Moles and moles cancel out, and K cancel out. You're only left with the units of liters. So now what do you get here? 5.25. Oh, sorry. Did everyone get this? 5.309?
Yeah, I did.
Okay. 5.309. Okay, that's fine. If you guys, because I was kind of rounding up. So volume of
0.39,
liters is 5.25 or 5.309, whatever, you know, you get, like that's, you know, it's also, that is also okay. Okay. All right. So these, and then the rest is you guys are going to do the remaining yourself, which is do the questions that relate to the Boyle's law, Charles' law, Gay-Lussac law, you know, so this one is like a little bit, you know, because it talks about, because you're being tested for the stoichiometry, whether you know the formula and whether you can do all these grams to mole conversions. Okay. So here, I'll just put here the other questions that you need to focus on. Look at now the Boyle's, Charles, Gay-Lussac, and then what's the other one? Avogadro, and then pay special attention to Dalton's law and special attention to the ideal gas law, ideal gas, and then the STP. Okay, so full-fledged, I would say that please look at the lecture notes for these, because we covered all this in great details there. Okay, so very important. And then just know the kinetic molecular theory, you know, those things are important. Okay, so this one, and then the rest part, I think you guys are okay. Then comes the chapter on, I'm going to just write on the important pieces here, because I know we are running late now. What was the other one? Other chapter is the chapter on the stoichiometry, the chemical reactions. Okay, chemical reactions. So we already talked about balancing equations, right? So that you guys can do on your own. I mean, just look at all these different types of reactions. If you're stuck, look at the lecture notes. Then the important piece here is, again, the reaction stoichiometry. Here, the reaction stoichiometry, and we are going to give you, definitely there's going to be a question on limiting reactants. Okay, limiting reactants, very important. And like I said, we have covered this in the class. So for now, if you want, if you're not confused, if you're still confused about something, I can do a specific question for you. But since we are now, you know, we've covered already stoichiometry quite a bit. So here is going to be limiting reactant. Definitely there's going to be a question. Limiting reactant and percentage yield. And if you want, I have this on the videos, you know, specific videos. You've just taken out those, and you know, you can look at those and maybe practice with me from there. Okay. So the question is definitely going to be, and then, you know, because mole to mole ratios, you know, grams to moles, moles to grams, all that has been covered. Then you should just know, you know, redox reactions, what are those, balancing equations, those we have already covered here. Next is going to be the, so I'm going to just put here, look at the redox reactions. Okay, that's also important. And then just balancing equations and all. So that's the chapter on chemical reactions. Then comes this other chapter, the intermolecular forces, chapter 6. Chapter 6 is the chapter 6 is the ionic and molecular compounds. Molecular compounds, and these molecular compounds are the covalent compounds. And in that, you will need to do the shapes, right? In this case,
Yeah.
what is important is the Lewis structures, do the Lewis structures, very important, Lewis structures, and do the shapes and polarity and intermolecular forces. And in these intermolecular forces, dipole, dipole, you should know dipole, dipole. London dispersion is present in all molecules. So London dispersion, and then you go, next is the London dispersion, then the hydrogen bonding. Hydrogen bonding. Very important. So remember that hydrogen bonding is only oxygen attached to hydrogen, nitrogen attached to the hydrogen that is attached to nitrogen, hydrogen that is attached to fluorine, hydrogen that is attached to oxygen. And we don't care what the rest of the molecule is. We don't, fluorine obviously is not going to be, it's just HF. So, but here it could be anything. It could be anything, R, 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 R dash. So it could be anything, but it's only this hydrogen that participates in hydrogen bonding. So always pay attention to that. Okay. So these things, and then obviously you will be tested on. Next part is this is the covalent molecular compounds. Then comes the ionic compounds. Ionic compounds nomenclature. There's going to be questions on that. Ionic compounds. So I'm going to put here, look at the lecture notes. Lecture notes. We covered all this in detail. Okay. So 1 or 2 questions are going to come. Like I said, on the exam, you know, we can only put so many questions. And so generally on the final exam, we test the, you know, your ability, your student learning outcomes generally, and I'm marking those important pieces right here. So stoichiometry is a big one. Okay, now here, this is also a very important piece, and this is also a part of your student learning outcomes, very important, and that is, can you write the names? Can you write the formulas? So all of the nomenclature. So I'm going to ask you to review that worksheet on nomenclature. Review that on your own, because you are going to get questions in which you will be asked to write the formula and of course the name, write the formula and the name. Okay, so how to write? So in this case, you should know, I cannot emphasize this any further, polyatomic ions and the charges. Okay, very important. You should just know this. So you will have these questions on the exam. Okay. And then what else is there? Yeah. And then the previous question, you know, chapter 1, you can ignore. Chapter 2, nothing major. Chapter 3, kind of okay. Chapter 5 is not, I'm not giving you anything from chapter 5. And then comes this chapter on the atoms, electronic. You know, the thing that you need to know here in this is the electronic chapter on atoms. In that chapter, you should know the, in this case, the chapters on atom is no electronic configuration. Electronic configuration, and also know the valency, okay, which is the valence electrons, right? And then also what is important is the trends in the periodic table. Trends in periodic table. And so what are those trends? Especially the trends that relate to the electron affinity and the electronegativity, okay? Electronegativity. What is electronegativity? So again, we covered this in detail in the lecture notes. And then the electron affinity. Okay, electron affinity, okay. So know these, and then there's just general properties, you know, metals, non-metals, metalloids, you know, you should know them. Metals, non-metals, metalloids. Which ones are these? Where are they in the periodic table? Just a general thing about the periodic table, right? You should know what are the, like what are the columns, what are the periods, and like what are they used for, like what are the, how are these placed? So those, so periodic table, just in general, like, you know. So I'm going to now end this, and I'm going to just put here that nuclear chemistry not included on final exam. Nuclear chemistry. So don't worry about the chapter 5. Okay, that's one thing. Second thing is that is what is not included. I mean, you can just skip chapter 1. And then, well, I mean, not really, like chapter 1 is what? What do I say?
Should be standard stuff.
Yeah, just some standard stuff. Just know.
Basic concepts.
Yeah, basic concept. Chapter 1, chapter 2, and chapter 3. What you should know? You should know scientific notation, right? Scientific. Just like we did.
Conversion factors, places, and place values. You should know units of measurement. How to properly convert.
Yeah, and then comes the, what is the other one? The significant figures, how to use them.
Yeah.
Significant figures and their problems, you know, relating to them. And then just general conversions, which we are doing, but I'm not going to give you convert like kilometers to meters or type of things. There's I'm also limited. So just know these, and then just know like basic things about like matter, you know, just basic things about matter, like solid, liquids, gases, you know, physical and chemical change, like those type of things. So just standard stuff you should know, you know. And I'm really, you know, we cannot, like I said, final exam is not, I mean, it's just to get your student learning outcomes in place. But really, you should know the content, your basic knowledge should be there. Okay, guys? So we covered quite a bit, and I appreciate how you all were very patiently listening and participating, and I hope that was helpful. And if you have any questions, you can, you know, ask me. I'm going to stop recording.
Professor?